All right. I'm going to talk to you all today about the ICON mission. This is an upcoming heliophysics mission led by UC Berkeley that's going to be looking at where terrestrial weather meets space weather. So this is a view of ICON, or artist image, orbiting above the Earth. Basically, think about the atmosphere. Think about the atmosphere that we breathe. As you go up into the mountains, it gets thinner. As you go up into space at the space station, it gets thinner and thinner. And you have this very tenuous layer that we call the upper atmosphere. It's at the top. And this green layer that you see out on the horizon, this is part of the ionosphere. So you basically have a thin layer within this thin layer that's ionized. And this is a space weather phenomenon. We have all sorts of, it affects things like satellite drag, communications, and things like that. It's very important for industry. But it's difficult to, it's more of a challenge to understand because you have this interaction between electric fields and the neutral atmosphere, and everything's connected through the geomagnetic field lines. So because we have this dipole field, you can imagine that you could have a thunderstorm in Tierra del Fuego, and this is driving space weather events that you would see over Boston. And so it's this large interconnected field, and we're really just starting to understand how weather from below is starting to drive the weather above. So primarily what we'll be looking at is airglow data from this. So basically the ions interact with the neutrals and they emit different wavelengths of light. So we'll have a green line down below, a red line, and then UV up above. And you can see for scale, the International Space Station is around 250 miles above the Earth. ICON will be flying a little higher up above that and looking with cameras down at these layers to understand how everything is varying with the drivers. So an example for this is what's driven below is if we just had the sun, if we didn't care about what was coming on from below, the ionosphere would look something like this. We'd have these peak layers on either side of the equator. It's fairly even with latitude, or with longitude. It's fairly even everywhere. But what really happens is we have all of this driving below. We see something that looks much more choppy, and this is because we're getting effects from the earth sciences side of things, from tidal effects in the atmospheres, because we have an uneven distribution of land and water, and so there's all of these effects in the lower atmosphere that propagate up and modulate what we see. And this is really a new discovery, and this is going to be very interesting when ICON gets up there and measures the winds and able to look at the connections and look at how in the lower atmosphere this is driving the ions on the field lines that are connected up much higher. An example of this was a recent study that was done looking at the effect of El Nino on the atmosphere. So down here we have the warm water in the ocean. This is driving and affecting the weather down below, and this can modulate the shape of the upper atmosphere. The warming effect down below results in a cooling effect up above because we're above the greenhouse. And so this changes the plasma distribution, and we see an example of an ionospheric enhancement over the Southeast Asian sector.